Christopher J. Stauber, and I'm going to be discussing the statistical modeling of wind power using a Gaussian mixture model. Here is some background information. There's been a big push from the government to move away from fossil fuels and to invest in research and development in regards to renewable energy, such as solar and wind. This paper that I'll be presenting talks about wind energy, but the applications of it could be for solar too, because the paper really focuses on utilizing statistics for modeling uncertainty within a wind turbine. And what is that? Like, uncertainty is the variance between, what the expected results are. Like, if something that you wouldn't expect to happens, like a huge gust of wind comes and causes, some mismanagement of the data, like that's the uncertainty that this paper seeks to model. So I'll go straight into the problem statement. So our problem statement is uncertainty within wind turbines has struggled to have been modeled with high levels of accuracy. A Gaussian mixture distribution has been employed to model this. Now, if you look at our equation, the U is the mean, and this symbol right here is the variance. And this is how they kind of model the function to go into our big equation, which I'll show. And this is their analysis technique. What they do is they use a distribution model, a Gaussian mixture model, to approximate the cumulative distribution function, and that is the uncertainty value at which we're discussing. And you kind of look at the equation here, and you can kind of see that it's a very, complex equation. How they get some of these values are theoretically divided or theoretically found, and some of them are empirically driven. And you kind of see like this is their very big function, Gaussian distribution. What I found really unique about this paper was its, very big approach using math, using like a combination of empirical data and theoretical derived data. That's something that I really loved. They did was they also took this paper, they also took this function, and they derived and then proceeded to normalize it using the least squared algorithm or method. And the next thing that they talked about was their data set. So their data set contained wind power forecasts and outputs collected over 2 years from February 2nd, 2010 to April 23rd, 2012, with around 77,800 samples. Like I said, these data sets were all normalized with 0 to 1 boundaries. And the predicted outputs from this model set are 0.5626. Now, one of the interesting things about the number of bins that they use is, I really like it how they got good with a very, set number of them. It's kind of when you're doing the statistical modeling, you want to give enough data so that you're able to get a curve close to what you're expecting it to be, but you don't want to overload the set. So you can kind of see how they start with a histogram here. You kind of see how it smooths out how the algorithm adapts to it. And I really do like that the author used a histogram. That wasn't something that I found within any other uh, papers that I was looking at. And one of the things that the paper mentioned was if the amount of bins is too big, the actual histograms within the PDF will be discrete, and it'll be difficult to fit within the distribution model. So the paper kind of affirms, kind of basic modeling theory where it says, you don't want to have too much data, but you also don't want to have too little data. So after we get into the data set, we'll get into the results. And this is the RSME values of the Gaussian mixture model, the Gaussian, the beta, and the versatile distribution. Now you can kind of look at the RSME, and the RSME basically shows, how close the model fit the data, like how accurate the data was. And he, ran these 4 studies, and you could clearly tell that, the the Gaussian mixture model was the closest. Now you could kind of look at like the versatile one, that was also low beta in the Gaussian. Some questions I had on this were one, it didn't really note the run times. It didn't give like a table of the run times, and also, it's always significant to have very good data. I just wish you could kind of do like a cost benefit analysis to know like the level of accuracy that you want. Like if this took, 16 hours of runtime to get, and this only took 10 minutes, you know, depending on your application, you might want to go with this one. That's something that, on my personal project, I'm taking a look at where, runtime is important, getting, 1 or 2% more accurate for 100 times more runtime might not always be accurate. And also other thing that I liked about the paper was that it gave the parameters of the approximation model with 10,000 bins, just to kind of reiterate what these coefficients mean. I'm sorry that I'm cutting it off. The K is the mixing coefficient for the ith component. This value represents the weight or proportion of the ith value of the Gaussian in the mixture. And, these are just standard, statistical. This kind of, the U stands for the mean, and the stands for the standard deviation. So you can kind of see here that, depending on what I value, you can kind of see the variability in the data. So like when the standard deviation is smaller, you get way more consistent data. So it's really interesting to tell, why I equals 1 is so much lower than like I equals 4, I equals 2. You can kind of see, another thing that I was interested in was, why are these two values so close? Another thing I wish she went to more if iterations, but obviously there was probably an issue with the runtime. Yeah, one other thing that I also liked about it was that I really liked that he ran other forms of study that, kind of went into to kind of prove his point that the Gaussian mixture model was the most accurate. One of the things that, I wish he maybe said in the paper was why the Gaussian was the least accurate compared to everything else, but the Gaussian mixture model was the most accurate. Just some food for thought and some questions I had. So that's everything. Feel free to ask me any questions, and we'll see you in the next video. Thank you. Take care. Bye-bye.